So let's start. So last time we talked about tensor product, right? If we have two vector spaces, over a field K, then we can talk about its tensor space. It's the set of all objects like this. Right? V-I-V, W-I-W, for I, and here is the positive integer. Or here, of course. Okay. Now, if E1 is a basis for V, and delta prime, let's say F1 up to Fn is the basis for W. Then we know the following, then the set EI answer at J, I from 1 up to N, J from 1 up to M is a basis for V tensor W. In particular, dimensions of this vector space is, of course, the number of elements here. How many elements do we have? Well, we have n sources for the first one, n sources for the second one, therefore this is dimension n times n. So the dimensions of the factors of the tensor product are multiplied. Okay. We proved this last time. It's in the book. I mean, if you don't understand, you may ask me. Yes. İşte eşit olamaz, onu söylüyor bu, değil mi? Yani ne söyledi? Bir daha söyle. Bu diyor ki olamaz, değil mi? Bu, so this is the basis. This is the basis means they are linearly independent. In particular, they cannot be equal to each other. So you don't remember the truth, I guess. Kind of? Nasıl?
Polinomları çarpıyoruz ya. Onu tensor product olarak tanımlayamadım. Çünkü özellikle
so polynomial algebra is a special tensor algebra, but they are not symmetric tensors. And so you are right, but it is not exactly tensors. But you are right. They are symmetric ones. And there are alternative ones, which we are interested in more, which I will describe later. Maybe should I talk about proof of this again? I did this last semester. it should be in your notes, but I forgot the details either, but I guess it was just you take bir dakika neredeydi o? Hı. Şöyle. İsterseniz birazcık bahsedeyim lütfen. Yani o bir neydi? So we have this lemma. So this is actually lemma 2 in page 48. And it's as follows. If so, F is a corrector, then the map by the formula which formula is well defined. Normal. Evet. Yok. Ben yanlış olmuş. Kovektör olduğu için onları hep starla gösteriyoruz.
Hocam,
Evet.
sol üst tahtayı gösterebilir misiniz?
Sol üst tahta.
Kısa bir süre. Teşekkür ederim hocam.
Bir şey değil. Hı. Şimdi çektim. Şey mi? Şöyle bir şey yapayım. Onu mu diyorsun? Düz çizgi.
Başka bir şey değil.
Ben de pek hatırlayamadım zaten. Evet. Kovektör olduğu için. Evet. Yani o bir şeyin starı değil. Kendisi star. Efendim? Yani evet tabii ki. Yani bir vektörün starı da var ama bu kendisi star. O yüzden hani E'leri, F'leri vektörler için, starları da kovektörler için kullanıyoruz. Ama bu hani bir vektöre karşılık gelen kovektör falan değil. Bu F star, adı o. Doğuştan star yani. Evet. Söyle.
Ben şey soracağım. F-star şimdi dual B'de ya.
Hı hı.
Ama herkesi o vektörleri şey olarak tanımadım. B'den Q'da giden.
Evet. Evet. Evet.
Şimdi B tensör W'dan W gidelim bir şey olarak.
Ha. İyi soru. Okay. Haklısın. So your friend is asking me, this F star means this F star is a map from B to K, right? But here I regard like this. That's why maybe we may call it different. Sen onu mu soruyorsun? Tamam, okay. March. Tamam. Sizin hafızanız iyi. Okay. Gerçi bu adam öyle bir derde girmemiş. Evet. Yani revize edilmesi gerekebilir de bence iyi bir kitap. Evet.
Burada da F-star'ın bir gerekmiyor.
F-star vektör uzayından skalar fiilden gider. Dual şey. Bu öyle. Evet. Bu. Bunu yeni tanımladım. Tamam mı? Şöyle tanımladım. So for this to be you have to prove two things. First of all, this is well defined. Second, it's a linear map. Kamerada kaldı. Evet. Okay, now why it is well defined? We have to show that this gadget takes the same values on equally regarded objects, right? So what we mean by equally regarded, for example, if we regard V tensor W, lambda tensor, so lambda times V tensor W, same as V tensor this, right? So I have to show that F bar star of something like this is the same as F bar star of this gadget. Because these two expressions as tensors are the same, but my formula uses this expression. What if I replace, this form with something equivalent? For example, if I have something like this, if I replace this by this one, will F bar star will take the same value on this one and on this one. So let's check them. F bar star on this side. Well, what is the value of this? According to my formula, you have to take F star of this vector and then just multiply that scalar with W. So this is X star of lambda V times W. But what is this? F star is already a linear map. Therefore, I can take this constant out. So this is just F star of V times W. Well, what about F bar star of this gadget? Well, by the definition, I have to take F star of this and then multiply it with the W part. Well, this is a constant. I can just take it outside. And I get this. And we see that they are the same, right? These two are the same. Therefore, at least for this equivalence, I am in good shape. But there is another type of equivalence, right? What is that? Well, we have also this. Let's say V1 cancel V2. Sorry, V1 plus V2 cancel W is the same as this one. Okay. So I have to prove this. F bar star evaluated on this object should be the same as F bar star evaluated on this object. So let's check that one also. F bar star V1 plus V2 cancels W. Okay, now how did we define this? Well, we defined it this way. Take F star of V part and just put it as a coefficient of the W. All right, so I'll take just F star of this and then W. Well, what is this? Well, by definition, sorry, F star is a dual vector. In particular, it's a linear map. Since it is linear, I can write it like this. Times W. This is a scalar multiplication, right? Because this is a scalar. And what is this? This is just F1, V1, W plus F star V2, W. There is no F1, just F star. Okay. But what about F star of this gadget? F bar star of that gadget. So let's also compute that one. F bar star V1 answer W V2 answer W. How did we define the value of this gadget? Well, we defined it this way. For each summand, I apply this, right? So that's what I'm going to do. For this summand, I will just do this. F star of V1 times W plus F star V2 times W. Well, it is the same thing as this one. Right? It is the same thing as this one. We get the same thing. Therefore, that thing is equal to this gadget. So this is just F star of V1 plus V2 cancel W. So what we see is that equivalent representations, if you use equivalent representations of your tensor element, F bar star will take the same value on each representation. Therefore, this is a well-defined map on the tensor product. Hence, from V tensor W, böyle miydi? Evet, buradan W is a well-defined map. We have to still prove that it's a linear map. F bar is linear. let's prove it. How can we show that it is linear? Well, we will take two elements of this vector space, put coefficients in front of them, and then we will just take f bar of that expression. Linearity is simple. So let's see. Okay, let's say lambda times a typical element of this. A typical element of that is something like this. We say, so lambda times this element plus some other element. L, summation over L, B prime L, W, L cross. Okay. So I take one element from that vector space, multiply with the scalar, and then I take some other element in lambda scalar. Now let's see what is this. So this is like f of lambda v plus or v1 plus v2, right? Now, what is this gadget? Well, this lambda comes inside and we get this. Sorry. Lambda k or more. Vk k plus the outside. I have two different sums, but I can just regard them as a single sum, right? And f bar star will act on this how? Okay. I can just use the formula for f bar star. F bar star will do the following. So I regard this as a single summation. For each term of the summation, f star will act on the v part. So f star plus, and then same thing for this part of the summation. F star v l prime w l prime. I write as a, two different sums, but actually you may just consider it as a single sum, right? So there is no problem with that. And what is this? Here, since f is linear, I can take this lambda outside. So, f bar of this digit, lambda k, v k, w k plus l v l prime w l prime is equal to. I can take lambda outside. Plus no, there's no product here. Just scalar product. Okay. Now, what is this digit equal to? Well, this is just lambda times f bar star of this digit. So Keshav, k plus f star of L d L prime w L prime. So we are done. What is that? You see, lambda times an element plus another element, its image under f bar star is equal to what? This lambda times this element plus f star of the second element. So this means f bar star is new. Okay. So
Öyle bir şey yapsak matematikçiler pişman eder mi?
eder. Evet. Yani şöyle, hepimiz anlaşırsak sorun yok da siz hani öyle bir anlayış vardır. Bizde hani ya onu hani aramızda şey yapacağız, nasıl diyeceğim, hani anlaşacağız. Ondan sonra öyle bir şey beklemem ama hani onu konuşmadıysak o zaman şey olur hani evet. Kitap da aslında onlardan bahsediyor da ben hani daha fazla karıştırmamak için yapmadım. Sorun değil yani o sadece bir şey conversion. Başka bir şey değil. Şimdi şeyi gördük. Bu madem bir lineerle o zaman şeyin ispatını yapabiliriz. Neydi? R transfer F J R from 1 up to M J from 1 up to M is linearly independent. Tabii bu basis olmak için yetmeyecek değil mi? I have to prove two things for this to be a basis. First, it is linearly independent. Then it's a spanning set. Spanning set part is easy. This one is the difficult part. Now, why this set is linearly independent? Well, assume that we have a linear sum of this term and this is equal to 0. Going from 1 to and came from 1. Diyelim ki bunların pardon ECF diyelim ki bunlar bir combination sıkıyor. Ne göstermem lazım? For this set to be linearly independent, I have to show that all these terms, scalars are zero. So must show this lambda jk's are zero for all j and k. And this is what we need to show. Let's see why that's the case. Burada şöyle yapacağız. Okay. Şimdi elimizde şey vardı ya, we called it E1, and right, is a basis for V. Let V1 star Vn star be the dual base. For this star, which is just homomorphism, right, from V to K. So, what are these elements? These are the following linear maps. E, J star applied to EI is equal to what? If it is the dual basis element, then this is either 1 or 0. If the indices are the same, it is 1, right? If I am the same, otherwise it is 0. So it is chronicle delta Ij, right? We just write it this way. And it is chronicle delta Ij. Now, these are, this star and that star are different. Right here, this E1 star means I have this basis, and then this gadget is the dual basis obtained from this basis. Okay. Now here for this F star, I will take this gadgets. E1 star, E2 star, and so on. Tabii ben kötü bir şey yaptım ama F star'ı hem orada kullandık. Neyse. Neyse, sorun değil. Şöyle diyeyim.
Gerisinden benim.
Yani
Gerisinden benim hocam. Şey.
neyse, önemli değil.
S artı M.
Okay, let's. I will take my F star to be E1 star. So let's take, for example, F star to be E1 star. Okay. And let's apply this digit to this summation. So E1 star, I will put a bar, right? Apply to this digit. Lambda, JK, EJ, and then F, K. Here, summation over all J and K. But this widget is just 0 by assumption. And since this is a linear map, this is 0. Well, this is a linear map. Therefore, I can write this as just take this summation outside And I can take this constants also outside. Lambda K. And then E1 star evaluated on this. Well, actually, I know how E1 star evaluated on this. How it is evaluated. E1 star will just eat this guy, right? The V part. And then you obtain a scalar and put it in front of, sorry, in front of the remaining part. And then the whole thing is equal to 0. Well, what did we get? What is this? This is E1 star EJ. This is 0 if J is not 1, and if it is if J is 1, it is 1. So this is 0 if J is 1. No, J is not 1, and it is 1 if J is 1. Well, that gives me what? So here J starts from 1 and goes up to n. For J is 1, this will be 1. For J equals 2, it will be 0. So there will be no term here. So this makes sense only for J equals 1. The other terms are 0. For J equals 1, what we get? For J equals 1, K stays here from 1 to n. J is 1. And then this is 1. And this is just Fk. And what we get is just 0. Right? The summation over J disappeared because there is only one non-zero term. For J equals 1, all others are 0. Therefore, this is what I get. But you see what we have here. These are basis elements for the vector space W. And I have some coefficients in front of them. And the whole sum is 0. But since this is a basis, I mean, if K's are basis elements, this is they are linearly independent. Therefore, this is possible only if all these coefficients are 0. So this means what? This means that lambda 1 K's are all 0 for all K from 1 up to n. Okay. My aim was what? My aim was to show that, remember, my aim was to show that all these coefficients are 0. And we managed to show that these are 0. But I can do all of them 0. How? But I obtained this by choosing X star, E1 star. If you choose this covector, E2 star, then you will get lambda 2 K's are 0. Okay? And then I'll choose F star to be E3 star, and that will give me lambda 3 K's are 0. And so on. Therefore, what I will get, all these coefficients are 0. Okay, so that proves that these are linearly independent. Buraya kadar tamam mı? İnanmıyoruz diyen var mı? Bizi kandırıyorsun diyen. Geçen dönemde inanmamıştık zaten diye. Var mı? Yok. Yani kandırdığım şeyler vardır da bu onlardan biri değil. Arada yoksa illaki vardı bir şey. Okay. So we proved that hence the set E R F J are from 1 up to m, J from 1 up to m is linearly independent. Why it's this spinning set? Görelim. So what I mean, every element of the tensor algebra, tensor vector space is a linear combination of these digits. But that is clear, right? So if V is in V and W is in W, then of course V is a linear combination of these digits. So lambda I times I, and W is just mu J times Fj for some lambda I and mu J. Then V tensor W is what? Well, it is, sorry, lambda I is I and then mu J of J. So there, well, this is a sum of several elements. This is sum of several elements. Tensor product will distribute right over summations because of the following. And if we have something like this, right? This thing is equal to this. And of course, you may do something similar here. So V tensor W1 plus W2 also to this one. Therefore, just using these two properties several times, we see that this is just summation over I and J, lambda I, mu J, I tensor Fj. So what we see is that any tensor product of this form can be written as a linear combination of these elements. So if I have a finite sum of these elements, that will be another finite sum of these summations, but that will be just another finite sum. Değil mi? Bunların son tanesinin toplamı olacak. Bu toplamların son tanesini alıp toplayacağım. Ama her birisi zaten bunların toplamı. Son tanesinin toplamı yine bunların toplamı olacak. Tamam? O yüzden de bu bir basis. Anlaşıldı mı? Okay. Bir de tabii ne vardı? Alternatif product. Yani So what was alternative product? So it's the belki aslında bundan önce şeyden de bahsetmek lazım tabii. Okay, let me before this, let me mention the following. Now we talk about tensor product of two vector spaces, right? But we may actually talk about tensor product of several vector spaces. For example, tensor product of V1 and V2. And then this is already a vector space. And I can talk about tensor product of this vector space with the tensor product of a third vector space. And then with the tensor product of a fourth one. And so on. Okay. We may consider such objects. And the actually kind of nasty part is the following. You may do this in different order. For example, I can first take tensor product of V2 and V3, and then take tensor product with V1, and then take tensor product with V4. Okay. So here first I take tensor product of this two, and I take tensor product with this one, and then with this one. Or I can do it this way. Take tensor product of these two spaces, then take tensor product of this with this one, and then with this one. This is actually something we have seen before. We have this kind of stuff when we consider Cartesian products also. For example, consider sets x1, x2, x3, and so on. Let me talk about just Cartesian product. x1 times x2, and then x3, x4. I can do things like this. First, take Cartesian product of these two, and then Cartesian product of these two, and then take Cartesian product of these two. Is this same thing as this one? Okay, I can do this. Well, actually, they are not the same things, right? What is it? What is a typical element of this? A typical element of this is just x1 comma x2. What's a typical element of this? x3 comma x4. And then typical element of this will be this gadget. So a tuple from this product, another tuple from this product, and then tuples of this. What about this gadget? Well, this is just x1, x2, and then you have Cartesian product with this. So we have something like this, right? This is the tuple. One element from this, one element from this, and then this is also a tuple. One element from this, one element from this. So you have something like this. Are they the same? No, I mean they are very different objects, right? But what we do in practice, we regard them the same, right? We consider them the same object. We say that they are naturally isomorphic. Although, you know, you may construct them differently. We just regard them as the same. And actually what we do, we just, instead of writing like this or writing like this, we just forget about the parentheses and write this as x1, x2, x3, x4, and write this as a formula. But you know, if you do everything carefully, then you have to actually consider, you know, this kind of stuff also. So when it comes to tensors, that becomes, of course, more important. What we do, actually similar to what we have done over here, we say that these things are naturally isomorphic. And we just do something like that, and we say that these are naturally isomorphic or canonically isomorphic, right? Burada tabii biraz diyeceksiniz ki yani el kol sallama var. Pek de matematiksel bir şey değil diye söyledi. Değil mi? Yani isomorfik diyorum da niye? Ama matematiksel olarak bu yapılabilir. Kanonik isomorfizm, burada isomorfizmi yazabiliriz. Here I can write down the isomorphism. How? I just send a typical element of this to a typical element of this one. How? Well, a typical element of this is what? V1 tensor V2, and then you take this digit and tensor with this digit. I regard this as a single element, and then take this thing as a single element and write tensor with this with an element here. I would just send this to where? Well, I would send it to the following: V1 tensor, V2 tensor from V3, and then take this as a single element and tensor with V4. So I can define a map like this. Then I have to prove that this map is an isomorphism. Yes. Sure.
Bir elemanın içinde toplam olacak. Bunlarla bir elemanın toplam olacak. Olmaz.
Evet, haklısın aslında, daha kalmış. Onları da böyle yazıldığını gösterip yapmak lazım. Bu bir yol. Yani buradan yazılabilir o. Daha ama iyi bir yol var. O da şey, bütün bu construction'ı universal construction dediğimiz ya da universal object dediğimiz bir şey var. O şekilde yapmak. Yani ondan bahsetmeyeceğim çünkü şey, yani quotient space vesaireyi falan kullanmak gerekiyor ama şöyle diyeyim sadece orders yani bu ne diyorsun? So-called universal cebir derslerinde göreceksiniz daha sonra. Yani orada şunu söylüyor. Bu tens diyelim ki mesela burada biz tensörleri tarif edeceğiz. Tensörlerden beklediğimiz özellikleri sağlayan bir tane cebirsel yapı kuruyorsunuz. Ondan sonra da gösteriyorsunuz ki o cebirsel yapıdan aptal izomorfizm bir tane var. Ondan sonra da bu türlü tarif edilen her şeyin de aynı özelliği sağladığını gösteriyorsunuz. Ondan sonra da işte şey yapıyorsunuz. Bunların hepsi aslında aptal izomorfizm aynı şey. Yani özünde farklı şeyler. Bu nesne ve bu nesne birbirinden farklı. Ama up to isomorfizm ve canonical isomorfizmle aynılar. Evet. Efendim? Olur. Tamam. Sen de onu mu soracaksın? Pardon, şöyle dersi başlatmadım mı ben?